As we continue in Chapter 11 on Topic 2, we're dealing with probability, of course, but it's events involving the word not and the word or. Now, this will tie into things we did way back in the beginning of the course. So let's look at the property now of probabilities. So in our introduction here, they're saying that often we may not know the absolute limit of something, so often we base what we observe on empirical probability, which approximates the true theoretical probability. And they give the example, it says, so far, no human has ever been known to jump higher than 8.5 feet vertically. So empirically, the probability of someone doing that would be 0, since that's not within the sample space. But that's not saying that someday that may not occur. So, we have our general formula for probability. The probability of an event is, again, our E stands for our outcomes that we're looking for from the sample space. So when we were flipping a coin, we had said that two fair coins, the sample space would be 4 items, and to get a heads would be 1 out of 4. Now, if we define our sample space with non-equally likely outcomes, as if we would always get both heads, or both tails, or one of each, here we're only talking about 3 outcomes. We would get 1 out of 3, which is incorrect, because we have to take order is not critical here, and therefore we get 2, a heads tails and a tails heads. So we had to add 1 to make our sample space 4. So in general then, as we think of this, our sample space has to be less than, or as we read it this way, 0 is less than or equal to, our sample space is less than or equal to 1. Now it could be 0 and it could be 1. Now remember, 1 is a whole, and this is the whole I'm referring to, which could be 2 over 2 or 36 over 36. All of these are equivalent. That's the one we speak of when we're talking about the whole out of 1. So it might be 1 out of 2, 2 out of 36. 1 is the whole, and 0, of course, is defined as 0. So generally we're dealing what's in between, not what's beyond that, what's not below that. Below that is negative, and above that is greater than the whole, which we don't have. Summarizing in words, the probability of any event is a number from 0 through 1 inclusive. That is, it could be 0 and it could have been 1. And that the probability is 0 is a possibility. And the probability that it's a certainty, that's going to be 1. That is the whole. And here is the properties of probability in summary, which we have just talked about. Normally, it's between 0 and 1. 0 probability, it's an impossible event, would be 0. Complete certainty, the probability is 1. And again, that could be 36 out of 36. We'll give you some examples as we look at example 1. And most are familiar with rolling a die, or if there's more than one, dice. This one's a good one to start off with because we know a die has 6 sides, and it's 1 to 6. So our sample space is 6. Now, what's the probability that a 2 is rolled? Well, there's 6 sides, so that a 2, one of the sides is 1. The probability of any of the 6 numbers coming up is 1 out of 6. Now, a number other than 6, that would be 5 out of 6. That the number 7 is rolled. Well, there is no 7, so the probability is 0. A number less than 7 is rolled. Well, it's going to be 6 out of 6, because less than 7 is 6, and there are 6 sides, so it'll be 6 out of 6, or 1. And that's what we see here illustrated. As we build vocabulary, we're now going to take a look at events involving not as a key word. Now, part of this was done in chapter 10, section 5, and we didn't do that. So we'll look at this whole chart. And again, you're going to see some old friends here, because we did set theory and operations or connective. The complement, we use this prime symbol. Remember, we had sets, and we had the universe out here. We had A was the members or the elements of set, and what was out here was a complement. That was what was not included in set A. So we had that symbol. And then in logic, we had the not, which was a wavy line. And in arithmetic, we use the subtraction sign. Now, the operation symbol or the connective, where we're talking about union, we had that special shaped U. In logic, we had the word or, and we had the upside down caret, and of course this is addition. We have a plus. Then for intersection, we had the inverted U-shaped symbol. The word in logic for intersection was and here we had the caret, and we're thinking here where they combine is multiplication. So we need to be a little familiar with that, And again, since you can use your notes, this will be a good thing to have. Now here, the rule for probability of a complement, and if we look at the Venn diagram, the complement of E is what is outside of E. And remember, where S is considered the universal item here, we think of it here as the sample space. So E complement is what is outside of what we're looking for. That is the rest of the universe. So we can find that by saying not E, that is the complement of E, is equal to 1, which was the whole, and what we've been doing for 1 in dice was 36 out of 36. That was the 1. We write it as a 1, minus then what is in the clear area, and that would be the probability of complement. That is event not E, the negation. So here's some of that old stuff is coming back. As we continue, again, the probability of E plus the probability of its complement of E is going to be the whole, which is 1. And if we looked at that Venn diagram, the whole thing is the shaded area and this clear circle. And that's what they're illustrating here. Now, if you are looking for the, just notice what's going on here, a little algebra. If you take the probability of an event would then equal 1, and then take this on the other side, that is, we transpose it, it becomes a negative. So the probability of the event is 1 minus its complement. Just another way of looking at this. I like it, the way they set this up. Very, to me, very clear, and hopefully to you. Now as we look at example 2, and we're looking at the probability of a complement, that is not something. When a single card is drawn from a standard 52 card deck, what is the probability that it will not be a king? Well, remember, your standard deck is 52 out of 52. Now that it will not be a king, how many kings are in a deck? Well, 4. So by using the probability of a complement, you end up with 48, this is a 2, 50 seconds. So there's our 48, 50 seconds. Now the way they're setting it up, again, this 1 sometimes can be a little confusing. The 1 is the whole. This many out of this many, if they're the same, is 1. And there's the formula. Let's do 3. In example 3, it's finding the probability of a complement again. Here we have 5 fair coins are tossed. Find the probability of obtaining at least 2 heads. Well, this is going to be 2 to the 5th power, and that gives you 32. So 32 would be your sample space. So if you did all of them, it would be 32 out of 32. And if you made a tree diagram, as they're suggesting here, only 6 of them would be the outcomes that didn't have at least 2 heads. So, in using the probability of complement formula, you're saying the probability of the event was equal to the whole. Now remember, the whole is 32 out of 32 minus the complement of E, that is, where you don't get at least 2 heads, which is 6. So 1 minus 6 out of 32 gives you 26 out of 32. Remember, you have to change this 1 to the whole 32 out of 32 so you can deal with fractions, and then you simplify, and there is your answer. You have found it by using the not, that is the complement. All right, we're going to look at events involving or now. Now, in defining or, we're going to look at another approach indirectly where we can consider the complements of an event. We had done that. Now we're going to use an indirect approach where we're going to say, well, there's one event, or, which would indicate the union of another event. That is, we're going to add. So let's take a look at an example. We'll take this in parts. Here's our sample space, which are the first 10 integers, 1 through 10, and we want to have numbers that are odd or indicates union are multiples of 4. So the odd numbers, as we define our set, are 1, 3, 5, 7, 9. So we have 5 out of 10 are odd. And since it's an or and it's union, we're going to add to it numbers that are multiples of 4. Well, we have 2, 4, and 8 out of 10, so that's 2 out of 10. So that will give us 7 out of 10 as a probability for letter A. Now, how about letter B? The number is odd or a multiple of 3. Now, if we did it as we did in part A, we have 5 out of 10, and then there are 3 multiples of 3, 3 out of 10. That would give us 8 out of 10, but that's not correct. That's incorrect. So this wouldn't work, and you might say, well, why? Well, it's because some of them are found in both subsets, so we don't repeat repetitions, or we don't use things that repeat. And reviewing something from chapter 10, it says they are not disjointed sets. See, in the one in part A, those members of one set were not in the other. Here we have repetition. So we have to subtract those that are repetitive, as is indicated by this formula. So when we add that together, we do get 8 over 10, but then we have to subtract the ones that are repeated, 2 over 10, and that gives us 6 over 10, which is now 3 over 5, which is the correct answer. So in probability theory, events that are disjointed are called mutually exclusive, and we see a little bit of here. These are disjointed sets. When they are connective and there is an intersection where items are repeated, in earlier lessons we said we had to subtract those out because they're counted here, they're counted here. You can't count them twice. Gives you the wrong results. So the official definition, they are mutually exclusive events if they are disjointed sets. That is, they have no events occurring simultaneously as they would if they overlap here. All right, let's take a look. So in summary, additional rules of probability for the events OR, remember that is a union or an inverted caret. So the probability of A or B is equal to the probability of A plus the probability of B, and if they are inclusive, there's repeating, we have to subtract A and B. If not, then we just have this part up here, and we can eliminate that if it's not, if there are no repeats and they are not inclusive. So in example 5, we're finding the probability of event involving OR. If a single card is drawn from a standard 52 card deck, what is the probability that it will be a spade or a red card? So this is a spade and this is a red card. So we have to first define our sample space. Well, our sample space, we said, is 52. Now, what are the events we're looking for? We're looking for a spade. That is, it's a of this suit, which is the spade, this symbol here. Well, within a deck, there are 13 of them. So that's sort of our first event. Or, we're going to do a plus here because it's union. It's a red card. Well, for a red card, remember there are diamonds. Again, you may not know cards well. And there are hearts. Hearts and cards that are shaped like so. These are called diamonds. I know that because I play solitaire. Well, again, there's 26 of these out of 52. So when you add these together, you get 39 out of 52. And when you reduce that, 13 will go into there 3 times, and 13 goes into there 4 times. So that's what we have. This one was easy. And let me also mention they are mutually exclusive events because these were all black and these were all red. In example 6, here we're treating unions of several components. It says Amy plans to spend from 1 to 6 hours on her homework. If X represents the number of hours to be spent on a given night, then the probabilities of the various values of X rounded to the nearest hour are shown in Table 5. Find the probabilities that Amy will spend in each of the following amounts of time. Now, if we were to add up all these decimals, this adds up to 1.00, which is 1, which is the whole of what she will spend. So, again, these are probabilities. So that she will spend fewer than 3 hours. Well, that's going to be 2 and 1. So we add up 1 or 2, that is 1 plus 2, will give us, you can see the bottom of it, as 15%, or 0.15. And before you flip the page, or I do the screen, B is more than 2 hours, so that would be these 4. More than 1, but no more than 5, so that will be 2 and up through, I guess it would be more than 1. Yeah, that's true. 2 and then 5. But we'll see it worked out on the next page. And then this last one, fewer than 5 hours. Again, you might say if it's fewer than 5 hours, here we're going to use the, in a sense, the complement. So in letter B, more than 2, so that would involve 3, 4, 5, and 6. We just add them up, and that gives us 85. In letter C, more than 1, but no more than 5. So again, we're adding up 2, 3, 4, and 5, and we get 80. Now in letter D, we could use the direct approach, but here they're going to use the complement rule, that here's the whole minus not fewer than 5, so that would be 5 and 6, and 5 and 6 is 10 and 15, which adds up to 0.25, so this gives us 75. Now again, you add up what's inside the parentheses as they're indicating, and we're using the complement rule. Okay, here they're giving you some background material on Table 5, and I had mentioned that all of the times, all of the probability of times add up to the whole, that is 100%. And this is a probability distribution for the random variables of time. Okay, example 7. Finding the probability of an event involving OR. Here we're going to take a look at, again, a deck of cards, that a single card drawn from a standard 52 card deck will be a diamond or a face card. Now here a diamond is going to be red. I could even color that in there. There we go. And how many diamonds in a deck? Well, there are 13 out of 52. Now, face cards. What's a face card? Well, it's a jack, a queen, again, I know a little bit about this, but not too much, or a king. These are called the face cards. The others are numbers, starting with 2 and then all the way up to 10. There's an ace in there too, but the face cards are the jack, queen, and king. So how many face cards? Well, there's 4 suits, 3 face cards, so this is going to be 12 out of 52. But now some of these face cards are going to be diamonds already, because they'll be the jack, king, and queen that we've picked out as diamonds in this column. So to get an accurate count, we have to subtract the 3 diamond face cards. And then this gives us 22 out of 52, which is simplified to 11 out of 26. So we see it in action there, where they are not mutually exclusive events, because in here we're going to have 3 diamond face cards. So we have to subtract that. The things they go through to make up examples here, this is sort of fun. Emily plans to enroll in one of 20 elective courses. She will choose them by throwing a dart at the schedule of courses. Well, anyway, if 8 of the courses are recreational, 9 are interesting, and 3 are both recreational and interesting, find the probability that the course she chooses will have at least one of these attributes. Well, here, these that are recreational will be 8 out of 20. Those that are interesting are going to be 9 out of 20. And 3 of them are both recreational and interesting. So since these 3 are either in one of these other 2, we have to subtract that. And then we end up with 14 out of 20, which gives us the 7 out of 10. So she's going to have quite a choice here, and hopefully she gets the course she likes. I'll tell you. And if we have time, and this was a shorter lesson today, we will go through some of these exercises.